Up to this point, we've used our ACLs strictly to block or deny packets, and there's certainly nothing wrong with that. But what we're going to do in this lab is a slightly different use, and we're going to permit or deny telnet access with our ACLs. We know how to limit telnet access with a one-size-fits-all password. We know how to create a username password database, and now we're going to tie it down to IP address. I want to give you a real-world application for this as well, because I found this to be handy. What I've liked to do in the past with some routers in my networks is limit access, telnet access that is, to other routers that were inside the network. So what you could say if you've got 3 routers in your network and you just want to be able to telnet to them from the other 2 routers and disallow any other address, is just do what we're doing here, write an ACL permitting those 2 specific addresses and then just denying everything else. We're going to do kind of the opposite here actually and deny one particular address. You might want to do that too, and then permit everybody else. So here we've got the VTY config, typical login, password, CCNA, privilege level 15. Let's go over to router 2 and make sure that we can telnet to that one, 172.12.123.3. And I'm prompted for the password, and there we go, and we're in. So obviously we're on the 172.12.123.0 network. Router 2 ends in .2, and that's the one we're now going to prohibit, because I want you to see what a prohibit caused by an ACL for telnet access looks like. So let's go ahead and write an ACL. Can we use a standard in this situation? Sure, because we're only filtering on source IP address. So I'll write access list 7 and deny. Let's use our host command, 172.12.123.2. We'll go ahead and log it, and that's it. Now, of course, the net effect of this ACL at this point is to what? It's to deny everything, because we have one explicit deny line, and then, of course, we have the implicit deny right below it. So we will get rid of the implicit deny, or negate it, with permit any. Since it's a standard ACL, we only need any one time. Now we need to apply it. And where should we apply it? To the VTY lines or to the interface that the telnet attempt is coming in on? We put this on the VTY lines. Just like login, just like password, just like privilege level 15. And let's see, if you go with IP access group 7, and they're coming in, so we'll go with that. You're going to get a caret pretty close to the front of that line. So it's basically the router telling us after IP, you are perfectly fine. So let's run iOS help to see all the options you have for your VTY lines. Don't mean to intimidate you, because you can go a long way without ever using a lot of these commands, but they are all still around. The one that we're looking at is right at the top. It's access class. Watch this on your exam. It's not access group, it's not IP access group, it is access class. Filter connections based on an IP address list. That's what we want. You still have to put the number, and you still have to put whether they're coming in or out, and obviously telnet connections coming in. And that's it. So let's go over to router 2 where we could telnet just a moment ago, and look at that. And it's connection refused by remote host. That's pretty generic, but it is saying the guy on the other end of this connection told you couldn't come in. It's actively being refused. It's not a wrong password. It's not a timeout. It's connection actually refused. That's what it looks like on the other end of an ACL that's been used by the access class command to protect VTY access. Really, that's all there is to the command. Nothing complex there at all. You know this is important because I'm using red font. This is the only time in the course I'll do that, unless I do it accidentally on another one, I admit. Because this question causes a lot of consternation among CCENT and CCNA candidates, and I am going to clear every bit of that consternation up for you right now, because I remember creating this section and adding it to a book I wrote years ago, because there's a bit of non-real world bit in here. And let me show you exactly what I'm talking about rather than a horrible description I just gave it. The number one rule of ACLs in the real world is to prevent traffic from traveling across a WAN when that traffic is going to be blocked from getting to its final destination in the first place. You really want to terminate traffic as early as you can. Even if this was not a WAN. Let's say the traffic was going to go through, 2 routers or 3 routers on a broadcast network. Well, there's no use in having the routers process packets and forward them if at the end of the line they're going to get dropped anyway. So this is where the confusion came in, because of course, logic says, hey, we want to stop the traffic as soon as possible so it's not going across links and it's not taking up bandwidth unnecessarily. Now, if we wanted to prevent this PC in this particular network from accessing the server on the other side of the WAN, logic certainly dictates that we would use an extended ACL and place the ACL as close to that PC as possible. Now, using the extended ACL allows us to specify a source and destination IP address, and that's really important in this case, as opposed to a standard ACL, which we certainly know by now only allows us to filter on the source IP address. And placing the ACL as close to the source of the traffic, it prevents unnecessary traffic in this situation from going across the WAN, but in any network, it just prevents it from being handled when it can't get to its final destination anyway. In this situation, if you don't want the traffic going to that server, why let it go across the WAN to begin with and then kill it on the other side? Using an extended ACL here, it stops the unwanted traffic from crossing the WAN and unnecessarily using bandwidth and the remote router's resources. If you have to use a standard ACL, you need to put it on the interface closest to the destination. And this is where the confusion used to come in. Pardon me. Because, first off, you'd look at it and say, why am I using a standard ACL to begin with? And even if you didn't think about the difference between the standard and extended ACLs, again, logic would dictate, I'm putting it as close to the source as I possibly can. But you couldn't do that in this network with a standard ACL, because that would block all traffic that was being sourced from that PC. You could not put it here, because then that PC would never be able to send any traffic. What you have to do in this situation, if you have to use a standard ACL, is apply it to the interface closest to the device that shouldn't receive traffic from that source. Now, of course, this gets me a lot of email, or got me a lot of email at the time. Why would I ever use a standard ACL here to begin with? And my answer would be, frankly, you wouldn't. Because if you were out of numbered extended ACLs, which does happen, we've talked about that, you simply write a named one. But if a practice exam question or a real exam question or a job interview question asks you about this, what they're doing is testing your knowledge of the standard ACL. Does this person know that you can only filter on the source IP address, and does this person know that a standard ACL should be put on the interface closest to the device that shouldn't get the traffic? Because again, if you put it over here on this router, the router on the left, and put it on the interface closest to that host, a source IP address of this host, if you're filtering on that, which is the only thing we can filter with a standard ACL, you're blocking all traffic coming from that PC. And that is not going to get the job done. Placement can also be affected just a bit when you consider how inbound and outbound ACLs handle traffic. Outbound ACLs are applied after packets have been sent to the outbound interface by the routing engine, but before they're actually put in the transmission queue. In contrast, an inbound ACL, it's applied before the routing engine handles them. So all things being equal, the router is better off by blocking traffic with an inbound ACL as opposed to an outbound ACL. But sometimes, like when you're stuck using a standard ACL to block traffic for some reason, the ACL has to go on the outbound interface. But again, if all things are equal otherwise, put it on the inbound interface, because that stops your routing engine from routing packets that are just going to get dropped anyway. Now we're going to tie all this together. We're going to have a standard ACL in our upcoming lab. We're going to have an extended ACL, and we're also going to talk about placement, because here is the network that we're going to use in the next lab. We've got a host device that I am using a Cisco router for. on the 11.11.11.0/24 network. We've got router 2 and router 3, and there's a WAN between them, 172.12.123.0/24. Router 3 has a couple of networks on the other end, a 33.33.33.0/24 network and a 44.44.44.0/24 network, where you can see we have an e-commerce server at .4 on that subnet. You can tell it's an e-commerce server because there's that great sack of money attached to it. So what we're going to do is start filtering that host device's access to that e-commerce server, because that's certainly a real-world situation. We don't just want anybody going up to our e-commerce servers. And then we're going to just make things, we're going to start with a standard ACL. And we'll talk about placement, then we'll work with an extended ACL on it. I'll even throw a named one in there. We're going to use all the ACL types really that we've talked about so far. So take a deep breath and we'll jump right into that lab at the very beginning of the next video. See you there.